name is Federico Errica. I'm a research scientist at NEC Laboratories Europe, and I'm part of the Intelligent Software Systems group. Today I want to present you our paper published at NeurIPS 2023, which is called on class distributions induced by nearest neighbor graphs for node classification of tabular data. This work tries to understand whether or not it is useful to build synthetic graphs, and in this specific case nearest neighbor graphs, when dealing with the problem of tabular data classification. The presentation is structured as follows. First, I'm going to introduce you to the problem by discussing tabular data, graphs, and how people transform tabular data classification problems into node classification problems. Then I will discuss some preliminaries, some background knowledge in order to show you why we did what we did in this paper. And after that, I will delve into the details of the paper. In particular, in part 1, I will discuss a theoretical toolbox that we designed in order to understand whether or not nearest neighbor graphs are useful for the problem we are interested in. In part 2, I will try to show you how the embeddings of nodes look like when we apply a very simple message passing architecture. And in the last part, I will discuss an empirical evaluation that we did to demonstrate that nearest neighbor graphs might not be a good idea after all. And this is also discussed in the conclusions. In machine learning, we are typically interested in classifying samples. In the simplest case, a sample can be just a set of features and it can have a class attached. In this example on the left, you can see that we have 6 samples and each sample will have either class 0 or class 1. In contrast, in graphs, we have typically a set of entities, here from 1 to 6, and these entities are interconnected depending on some structural relationship. Colors here indicate that the nodes 1, 4, and 6 belong to one class, whereas nodes 2, 3, and 5 belong to another class. In recent times, people have tried to investigate the construction of nearest neighbor graphs starting from a table in order to transform the original classification problem into a node classification problem. The question we want to address in this paper is it really helpful? And we know from the literature that in the semi-supervised setting, when you only have a small portion of labeled examples, this construction can be useful. And this is probably related to the regularizing effect of k-nearest neighbor graphs or nearest neighbor graphs more in general. But what happens when we are in the fully supervised setting, where we have enough training labels? Is it really the case that the k-nearest neighbor graph is helping us, or is it introducing noise? To answer this question, we first need to understand when a graph structure can be considered helpful for the task. For this reason, we consider the cross-class neighborhood similarity, or CCNS, which was introduced by Ma et al. At ICLR 2022. The CCNS constructs a matrix of size number of classes times number of classes, and each entry of this matrix compares the distributions of the neighboring classes of nodes of class C and nodes of class C prime, where C and C primes are the entries of the indices of the entry of this matrix. Of course, you can consider similarity or dissimilarity metrics. That is not really important, but what is important is that if the CCNS has a diagonal shape, then the graph is considered to be helpful. And the reason is that nodes of the same class will have similar class distributions, and therefore their node embeddings will be similar compared to the node embeddings of a different class. However, if the interclass similarity is also high, then nodes will be harder to distinguish between different classes, of course. This matrix relies also on the assumption that if two nodes belong to different classes, then their distributions over the features are different, which is a pretty strong assumption on graphs, but not that much for tabular data. Actually, this is exactly what you expect from tabular data. So at this point, the question becomes, what does the CCNS look like for nearest neighbor graphs? And this is what we try to understand in our paper. The first part of the paper is devoted to develop a theoretical toolbox to understand how the CCNS matrix looks like for nearest neighbor graphs under a given data model that you see here in the picture. So in particular, we assume that each point, each sample of a given class C is generated from a Gaussian mixture model, which can approximate almost any continuous distribution. And for instance, you can have a look at the picture on the right, where we show two different class conditional distributions, the green one for class 0 and the blue one for class 1. So let's continue with this example and assume that we know exactly the shape of the distribution P of x. Of course, this is just for theoretical purposes. The first result of our paper states that we know how to compute the distribution over the classes of neighbors of a given point x. And the intuition is simple. If you observe in the picture the sample xu and you construct an interval, you take into account the interval of size epsilon centered at x, then it's evident that the area, the blue area, which belongs to the conditional distribution P of x given c equal to 1, is far greater than the area corresponding to class 0. This means that if I look at my neighbors around xu, it's more likely that a node of class 1 will be present than a node of class 0. And this intuition can then be, let's say, improved by averaging these quantities over all over all points of class C. So we get like an aggregated estimate of the neighboring distribution, the neighboring class distributions of points of a class C. And we can use this in our last step, to approximate the CCNS for nearest neighbor graphs, either through a lower bound approximation or via Monte Carlo integration. And here I have an example for you where we picked a random data distribution and we computed the k nearest neighbors graph for k equal to 100. Of course, our approximation gets better as the k increases. And as you can see, there is almost no difference between the true CCNS matrix on top and our Monte Carlo estimate at the bottom. But this also means that the CCNS doesn't look great for nearest neighbor graphs. And we tried this with many different randomly drawn data distributions. So can we try to understand a bit better what's going on here? We therefore move to a better understanding of how node embeddings look like in a message passing architecture, and for simplicity we consider a one-layer neighborhood aggregation where the embedding of a node HU is computed as the mean of the feature vectors of the neighbors. If we consider a k nearest neighbor graph, we obtain in our paper that the distribution of the embedding HU, knowing that the input features of node U were XU, is simply the Gaussian, a Gaussian distribution centered at XU with diagonal covariance matrix lambda epsilon. So epsilon is again the length of the interval that we want to consider. It follows from this result that we can compute class conditional embeddings. So we can give like the exact shape of the node embeddings of a given class. And surprisingly, this distribution is again a mixture model, which is almost identical to the original class conditional P of x given C, with the addition of this covariance term lambda epsilon. And this lambda epsilon has the effect of spreading the distribution a bit more. So intuitively, one would expect that the distributions of different classes in the embedding space would look more overlapping. And to test this, we compared the divergence, some divergence metric, which we can compute in analytical form, between P of x given C and P of x given C prime, and the same divergence but in the embedding space, so between P of h given C and P of h given C prime. And here we get another negative result. So the divergence in the embedding space is always lower than the divergence in the input space. And this means that the embeddings of different classes are less separable and therefore less easier to classify than in the input space. So this again shows that k-nearest neighbor graph in this case is not really the best solution. It doesn't appear to be the best solution to help us in improving the classification performances compared to using a simple method for tabular data. And this is exactly what we want to show in our empirical evaluation. We compare structure agnostic and neural network for graphs on a big set of data sets. We have 8 data sets from the UCI repository, which are by nature tabular, but we also consider 3 popular graph node classification data sets, Cora, Site0, and PubMed, where we removed the original graph structure and we replaced it with k-nearest neighbor graphs. In all of these data sets, we consider the parameter k as a hyperparameter, and you can find a detailed table of all hyperparameters tried in the paper. But the main result here is that under the fully supervised setting, so when we have enough training labels, a multilayer perceptron is always better and never worse statistically than the graph-based models. So that puts under question whether or not it is really helpful to convert a tabular classification problem into a node classification problem by using k-nearest neighbor graphs or nearest neighbor graphs in general. And this brings us to the conclusions of the presentation. We hope to have shown you that whenever you have enough training labels, converting your tabular data classification problem to a node classification problem through a nearest neighbor graph construction might not be the best choice. And the result is supported by the theory we developed as well as by the empirical arguments. But most importantly, what I would like to leave you as a take-home message is that this is a field that is very much underexplored. We need alternative graph construction techniques if we want to, if we hope to actually gain some practical advantage from using deep graph nets on these tabular data classification problems. And I invite you to study this problem. Thank you for watching, and feel free to contact us if you have any questions.
Orchestrating a Brighter World, NEC.